In the previous video, we covered molarity and mass concentration, as well as the modification of a solution's concentration via concentration and dilution processes. Today, we're going to introduce solubility. To start with, we need to understand that solvents cannot dissolve an unlimited amount of solute. There is a limit to how much they can dissolve. This is easily observed if we start dissolving salt or sodium chloride in water. At first, the solution will look something like the drawing in the middle, but over time, as more and more salt is added, the salt will stop dissolving and will begin to gather at the bottom of the container. This is solubility in action. Salt likes to dissolve in water, but there's a certain point at which the water is simply incapable of dissolving any more sodium chloride. This is the concept we're going to elaborate on today. Most people probably have a general idea as to what the term solubility is referring to. Solubility is essentially a measure of how easily a given solute dissolves in a given solvent. This means that for any particular solute, it will dissolve more easily in some solvents and less easily in other solvents. When a solute dissolves easily in a solvent, we say that said solute is soluble in the solvent. So, for example, we can say that sodium chloride is soluble in water because we know that salt dissolves in water without much coercion. The opposite of this, when a solute doesn't dissolve easily in a solvent, we call that solute insoluble in said solvent. However, like polarity, which we discussed in a previous unit, solubility is not a binary. It's actually a spectrum. A solute can range from being extremely soluble in a solvent to being practically insoluble, or anywhere in between. Unlike polarity, solubility is quite easy to quantify. We measure solubility in terms of concentration, and it shares units with concentration. So, the recommended units are grams per liter, moles per liter, and so on. Now, when the concentration of a solution is lower than the solute's solubility in that particular solvent, the solution is said to be unsaturated. When the concentration reaches the solute's solubility, the solution is said to be saturated. We might sometimes hear this referred to as the saturation point, since it is impossible to continue dissolving more solute past this point. Finally, when the concentration of solute is higher than the solubility, we call the solution a supersaturated solution. Supersaturated solutions involving a solid solute will result in an amount of precipitate forming at the bottom of whatever container the solution is being contained in. This is what we observe when we add a large quantity of salt to a small quantity of water. The salt that refuses to dissolve represents the precipitate that forms because the water and salt solution is too saturated for any more sodium chloride to dissolve. Before we get too invested in this illustration of salt being dissolved in water, we should remind ourselves that not all solutions involve a solid solute in a liquid solvent. A solution is simply any homogeneous mixture in which the particles are too small to see or to be separated. This means that something like brass, an alloy of metals, is actually a solid in solid solution. Air is another example. It represents a gas in gas solution. It's obviously somewhat harder to imagine a gas being dissolved in another gas, or a solid being dissolved in another solid, and because of this, we're going to set new definitions to the terms solute and solvent. From now on, the solvent is the substance that is present in the largest amount, as measured in moles, whereas the solute or solutes are the substance or substances that are present in lesser amounts. Based on this new definition, let's look at this conceptual problem. Example 1. Identify the solute or solutes and the solvent in air. The solvent is present in the largest amount in a solution. We probably know by now that nitrogen comprises about 78% of atmospheric air here on Earth. So diatomic nitrogen is our solvent. Our solutes are, essentially, all the other gases present in air. We have oxygen, O2. We have water vapor, H2O. We have the noble gas argon, or Ar, as well as all the other trace gases we're not going to list. A major question chemists try to answer in regards to solubility is the question of what factors affect a solute's solubility in a given solvent. In order to get a clear answer, we have to examine solutions on the molecular or atomic level. In other words, we have to zoom in on solutions. When it's all said and done, the ability of a solute to dissolve in a solvent comes down to the intermolecular interactions between the solute molecules and the solvent molecules. The stronger these interactions, the more easily the solute will dissolve in the solvent. The weaker these interactions, the harder it will be for the solute to dissolve. More specifically, these interactions are attractive in nature. So, to put it simply, more attraction equals higher solubility, and less attraction equals lower solubility. From this, we can revise our previous question. We now ask, what factors affect the interactions between solute molecules and solvent molecules? There are two groups of factors. The first are the so-called environmental factors. Temperature, for example, generally makes gaseous solutes less soluble as temperature rises. There is an inverse relationship between temperature and the solubility of gases. For solid solutes, on the other hand, the opposite is true. There is a direct relationship. When temperature rises, the solubility of most solid solutes increases. Pressure only has a measurable impact on the solubility of gaseous solutes in liquid solvents. A higher pressure makes most gases more soluble in a liquid solvent. By the way, we are going to assume that pressure is a well-known concept, but if anyone out there is confused, pressure can be concisely defined as the force applied to an object over a certain surface area. When we talk about solutions, we're usually referring to atmospheric pressure. Earth's atmosphere is made up of many different gases, and these gases push down on all objects here on the Earth's surface. This downward force is what we experience as pressure. This same idea applies when we talk about water pressure. This is a major concern when it comes to ocean exploration. When a submarine or other vessel goes deep enough, the water pressure can be so great that it can crush the submarine itself regardless of the material the ship is made of. This is because the deeper we go, the more water is above us, and that water is exerting a huge amount of force on anything submerged in it. That force is what we call pressure. We'll explain the reasons behind pressure's impact on solubility in just a little bit. Aside from temperature and pressure, we have two other factors, and these are what we will call molecular factors, since they have to do with the chemical properties of the solute and solvent molecules. The first of these is molecular size. There are two trends that have been observed regarding molecular size and solubility. Generally speaking, larger molecules dissolve less easily than smaller molecules, so there is an overall inverse relationship between molecular size and solubility. We'll discuss the opposite side of this in a little bit. The second molecular factor, and the more significant of the two, is polarity. The relationship between polarity and solubility is best described by the axiom, like dissolves like. What we mean by this is that polar solutes dissolve most easily in polar solvents, and nonpolar solutes dissolve most easily in nonpolar solvents. As a matter of fact, some nonpolar solutes are almost completely insoluble in polar solvents, and vice versa. Of course, having established these factors as affecting solubility, we now want to ask ourselves why that is. Why do temperature, pressure, molecular size, and polarity impact solubility? Again, we have to look closely at solutions to answer this, so here we go. Whenever a solute is added to a solvent to form a solution, this is what happens. First, the solute molecules move away from the bulk amount. Down here, we have a beaker of water to which sodium chloride is being added. Sodium chloride is drawn in white and water in blue. The dots represent molecules of these compounds. The bulk amount of sodium chloride is the mass of white molecules we see up here. Once the sodium chloride hits the surface of the water, the molecules begin to spread out. This is what we mean when we say they move away from the bulk amount. They stop existing as a large mass and begin to spread out. Following this, these solvent molecules begin to approach the solute molecules and try to interact with them. If the intermolecular attractive forces are strong, these solvent molecules form a sort of ring around individual solute molecules. This isn't always a perfect circular ring in real life, but this is the general idea. The solvent molecules are isolating the solute molecule away from other solute molecules so that they can interact with it freely. This is what happens whenever we dissolve anything. We're looking at a solid in liquid solution here, but the same occurs in any kind of solution. If we expound upon this knowledge, we can start to draw connections between the intermolecular attractions that drive solubility back to the 4 factors we discussed earlier. Let's begin with temperature. Temperature affects the solubilities of solids and gases differently. For gases, a higher temperature makes the gas molecules more excited. They start to move around erratically thanks to the energy the additional heat is giving them. This means that they will actually try and escape the solution and fly away into the surrounding environment, thereby decreasing this gaseous solute's solubility. For a solid solute, this added energy actually helps the solute molecules move away from each other, giving them enough energy to overcome the attractive forces that are holding them together. Once the solute molecules have been spread apart, of course, they are more free to interact with the solvent molecules instead. This is why a higher temperature generally increases the solubility of solid solutes. Pressure, as we stated earlier, only has a measurable effect on gaseous solutes in a liquid solvent. This is because more pressure forces the gas molecules to stay contained inside the solution rather than escaping, effectively having the opposite impact to that of higher temperatures. This is why a higher pressure usually correlates with a higher solubility for gaseous solutes. Now, we mentioned earlier that there's another side to the impact of molecular size or molecular weight on solubility. On the one hand, a smaller molecule is more easily surrounded by solvent molecules, which should mean that smaller solute molecules will dissolve more easily than larger solute molecules. At the same time, however, a larger molecule also has a larger surface area, and a larger surface area means that there is more room for the solvent molecules to form attractive forces with the solute. Because of this, molecular size can either increase or decrease the solubility of a solute, which, as you can probably imagine, makes it a poor indicator of solubility in general. Last but not least, we have polarity. If we remember from our discussion on polarity, we will remember that polar molecules are the result of large electronegativity differences between atoms. A molecule like sodium chloride is polar because chlorine is far more electronegative than sodium. This disparity creates different regions on the molecule itself. Some regions are more positively charged, and others are more negatively charged. This means that when we mix two polar compounds together, the positive regions of one type of molecule will begin to interact with the negative regions of the second type of molecule. Opposites attract, as we've said many times. This means that polar solute molecules are going to have strong attractive forces between them and polar solvent molecules. But these same attractive forces do not exist when a polar solute is dissolved in a nonpolar solvent. These are but two examples. On the left, we have a solution of sodium chloride in water, and both of these substances are polar, meaning that the former is soluble in the latter. On the right, we have this isn't actually a solution, but it is a mixture of oil and water. Oil is a nonpolar substance, and water is a polar substance. As we know, oil and water do not mix. There just isn't enough attraction between water molecules and oil molecules for that to happen. At the same time, we do have to append our usual disclaimers. All of the before-mentioned factors represent general trends, which means that there are always exceptions. This is one of those things that can be very annoying when studying chemistry, but it is the reality, unfortunately. Some substances have odd properties that enable them not to follow the trends we've established regarding their solubilities, so we shouldn't be surprised when we encounter these exceptions to the rules. In addition to this, we should remember that temperature and pressure are the factors which most directly impact a given solute's solubility, which means that they are the factors that are accounted for first by chemists studying the solubility of a particular compound. Both temperature and pressure can be changed in a laboratory environment, obviously, and most compounds dissolve very differently at different temperatures and pressures. This is what we mean by these two conditions having the most direct impact on solubility. There is another word frequently thrown around when discussing this topic, and that is miscibility. A substance is said to be miscible with another substance when they can form a solution when combined in any proportion. In other words, we can keep on adding substance A to substance B, and they will continually form a solution no matter how much of A or B we add. This is related to but distinct from the concept of solubility. Solubility makes a reference to the saturation point, and from this we know that once there is enough of a solute, the solvent won't be able to dissolve any more of said solute, and the solution will no longer be a homogeneous mixture. We can also measure solubility quantitatively by setting a concentration value to it. The concentration value we set represents the saturation point. Let's say, for example, that we are looking at the solubility of copper sulfate in water. I don't have a value for this off the top of my head, but let's assume it's some number x. This variable has units of moles per liter. If we were to fill a beaker with water and then started adding copper sulfate, the solubility of copper sulfate in water at the room's temperature and pressure would represent the maximum amount we could add. If we continued adding copper sulfate so that the concentration of the solution is higher than the solubility of copper sulfate, the leftover copper sulfate would start to gather at the bottom of the beaker rather than dissolving. Miscibility, by contrast, is not a quantitative value. Rather, it's a qualitative value. When someone asks, what is the solubility of copper sulfate in water at a temperature of 100 degrees Celsius and atmospheric pressure, we can give them a numerical answer. We can say, the solubility is 3 moles per liter. That's not the actual value, but it will be some numerical value that we can look up in a reference book or on the internet. But if someone were to ask us, what is the miscibility of copper sulfate in water, our answer would either be, it is miscible, or it is immiscible. We can't quantify miscibility the way we can with solubility. That's the major difference. One example of miscibility occurs between ethanol and water. Ethanol is also known as drinking alcohol because it's the compound responsible for the effects of wine, beer, and other alcoholic beverages. Ethanol is miscible in water, and the two compounds will form a solution in any proportion. In our next video, Unit 4, Video 4, we will cover colligative properties. Thank you for watching.